In order to do this, we have to deal with keto-enol tautomerism. We dealt with this in the first semester, but let's look at it in detail right now. Remember, if I have any carbonyl compound, right, if there is an alpha hydrogen, and I really need to say a carbonyl with an alpha hydrogen, that's a little more accurate, it will equilibrate between the keto form and the enol form. So you can look back to section 8.4, you can look in Chem Activity 11 in our POGO book to talk more about this. This is an equilibrium between two different compounds. Tautomers are separate compounds. They're not resonance forms. Remember, for it to be resonance structures, you have to have all the same atoms in all the same place, and the only thing you're moving are electrons. Okay? But this is different, because look what moves here. In the keto form, we have an alpha hydrogen. In the enol form, that same hydrogen is now attached to the oxygen. So atoms have actually moved. We have two compounds that are in equilibrium with each other. An excellent way to track this down is to find the OCC group, right? In the keto form, it's O double bond C single bond C. In the enol form, it's O single bond C double bond C. Like that. So track the fate of the alpha hydrogen. It was on the alpha carbon in the keto form, now it's on the O in the enol form. The double bond also migrates between the CO in the keto form to the CC in the enol form. So we have this 3-atom unit here where everything sort of swaps from one end to the other. It happens that in most carbonyl compounds, the equilibrium strongly favors the keto form, because in nearly all compounds, the CO bond is more stable than a CC bond. We've talked about that before. Okay? So in cyclohexanone, we have greater than 99% keto form. In acetone, it's even more than that of the keto form. Now, there are some stable enols. We've seen one of them. If we draw phenol, it's benzene with an OH. We don't usually think of it as an enol, but it is, right? If you look at the OH and it's attached to the ring, but the OH is directly on a double bonded carbon. So technically, that's an enol. That is at equilibrium, actually, with its keto form, but in this case, the enol form is strongly favored. Why? If I drew the keto form of phenol, I have two double bonds in the ring that remain the same, but then I'm going to migrate this double bond that the OH is attached to and make that become the carbonyl, and I now have two H's on the alpha carbon, where we had just one H on the aromatic carbon next to the OH. So hopefully by now we can see why this equilibrium would favor the phenol, because it is aromatic, where the keto form is non-aromatic. Okay. We're afforded that extra aromatic stability by having the 3 double bonds within the ring. That's typical of other aromatic compounds, not just phenol. There are times when having a double bond in the ring there makes it aromatic, whereas having the C double bond O as a tautomer makes it non-aromatic. So tautomerism can happen by acid or base catalysis. To draw a mechanism, we have to have one or the other present. So an acid catalyzed, we got to start it just like any other acid catalyzed carbonyl reaction, which means what? Means the carbonyl oxygen gets protonated first. So if I start with the keto tautomer, the O gets protonated, reacts with whatever acid catalyst is present, right? These O lone pairs attack the H of the acid, whether it's hydronium or HCl or whatever. Okay? We have a protonated carbonyl, which is in resonance with a carbocation. If I make the double bond electrons jump up onto that oxygen, I have a carbocation. In either case, you can do that from either resonance structure now, where water or the conjugate base of the acid we used will attack an alpha hydrogen in order to shift the CH electrons into CC to become that double bond. That's how the enol is formed. We can draw water or the base attacking whichever resonance structure we want. Okay? That's always going to be the case when we have two important resonance structures. We can use either one of them in our mechanism. Remember, because these two resonance structures are the same molecule. Okay? These are just two different ways of drawing it for us. The molecule itself is a combination of those. So what we could do is have water or the base attacking the alpha hydrogen of the protonated carbonyl form, where the CH electrons move to become CC double bond electrons, and that pushes the CO electrons up onto the oxygen from the double bond. So either one of those is acceptable, but in either case, we end up with the enol tautomer. So remember the steps. Protonate the oxygen first, then remove the alpha hydrogen. Now, they remind us here that removing a hydrogen next to a carbocation is an E1 reaction, right? That's a first-order elimination that involves that carbocation. So in a standard E1 reaction, we would have had a leaving group that left on that carbon to make that carbocation. But here, we have this C+, and our base or whatever removes a hydrogen next to it, and that puts CH electrons towards the C+ to make that double bond right there. The end result of this is a net proton transfer from the alpha carbon to the oxygen, okay? And it's also a migration of the double bond. So if you're asked to draw the mechanism, you of course have to draw the mechanism with each arrow, but if you're not asked specifically for that mechanism and you're told that you can abbreviate proton transfers, you can always just say, here's acetone, I'll draw that at equilibrium with its enol tautomer. Okay? You can just abbreviate that. Just like that, because it's essentially a proton transfer. Okay. The base catalyzed mechanism is another way that we can go. We'll talk about this in detail in just a few minutes, but alpha hydrogens, it turns out, are slightly acidic. They have a pKa of around 20, so they're not as strong as alcohols, but stronger than things like amines or just regular CH bonds. So if I have a base catalyst like hydroxide, that can attack an alpha carbon, and it forms what's called an enolate ion. That's this. So if we just directly put those CH electrons onto the C, we have a C- on the alpha carbon. That's called the carbanion resonance structure. But that's in resonance with, if I take that C- and make a double bond that kicks electrons up onto the O, that's in resonance with the O-, or with the oxyanion resonance structure. Both are the same thing. There's only one enolate ion. It can be represented in either of two ways. So once we have the enolate ion, it's just a simple matter of the O of the oxyanion resonance structure attacking an H from water or whatever, protonating the O, giving us the enol tautomer, and that regenerates the hydroxide catalyst. So base removes the alpha hydrogen. That makes an enolate ion, and then the O is protonated. That's it. It happens that alpha hydrogens are acidic because the resulting carbanion, right, this alpha carbanion, is resonance stabilized. This C- can be distributed onto the O-, right there. So it's essentially two resonance structures. The carbanion. So one arrow with two heads, right? Double-headed arrow to either resonance structure. The O probably bears more of that negative charge because the oxygen is a little more electronegative, but really, both of them, both the C and the O, have a significant partial negative charge to them. So if I were to try to draw a hybrid of that, it would look something like this, where I have a half-formed double bond between both the O and the C, and then partial negative charge on the C and on the O. That's the resonance hybrid of the two. And that's probably what an actual enolate ion would look like if we could see it.